So I want to describe what we're going to do for project 3. And first I'll just say what we're going to do at a high level because it's very simple. Um, when you put an input into DES, there's an initial permutation and then you have 16 rounds. And for each round, the Feistel network has a left half and a right half, and both are 32 bits. So the total state in a given round is these two things together. So what I want to do is look at what happens if we take two different plain texts that differ in just one bit and then follow them both through with the same key and look at the differences in the bits round by round. And then I think what we'll see is that there will be only one bit of difference at L0 and R0, and then by the output we generate, we'll look and see how that one bit of difference explodes into several bits of difference. And I haven't done it myself right now, but I think after 5 rounds they'll be completely different. So I've written some code to get you started. This is what you'll see in your folder or something like it. I might take out this executable and stuff. Let's look at main.c. So here are some instructions for compiling this code. There are several different C files in this directory, and they all have to interact together. And so this just gives you a short note about how to link them all. It would be probably good exercise to do that step by step, but this will work. So this what's in main right now just tells you how to sort of call DES. The DES that we're going to use is the DES in the C file, not implemented by me. There's you can read the notes and see where it came from. Unfortunately, it's very hard to understand because it's highly optimized. But on the other hand, I couldn't get the other DES code is simpler, but I kept getting segmentation faults, and I know this works anyway. So first you decide what the key will be, and so this print statement uses a command that converts binary to hex. So the key is 8 bytes, but it's gonna, in general, it'll be 8 unprintable bytes, and so it can be convenient to look at the hex instead. I'll say some more about that in a minute. Here is the key schedule. If you look at the description of DES, there's a key schedule. For each round, there's a different 48-bit subkey. So you have to set the key schedule here. Now it's contained in this little struct that's defined in DES56.h. You don't have to worry about that. Here's some plain text, just random 8 letters, and print it for the user. And this is the thing that calls the actual DES. So this does one block of DES encryption on the plain text. If you put a 0 there, it encrypts. If you put a 1 there, it decrypts. So that is just encryption. You don't have to do any decryption for this project, and you have to pass the key schedule along. Then the ciphertext is overwritten with the plain text is overwritten with the ciphertext, and I convert that back into, I convert it into hex because it will just be unprintable garbage. So let's run this program and see what it does. And I'm really having having a hard time with CodeCalc today. This terminal over here is not running in this directory, but they have the same name and the system is confused. So I'm going to remove this stupid thing and just make a new one. I guess I better name it something else. Alright, so let's compile everything. First let me do it wrong. So if I just compile main.c, it will give you linking errors. So you have to compile all the C files at once. You could write them all out at once if you wanted to. And hex.c, those are the 3 files you need. But a simple way to do the same thing is to use the Unix star notation. So what this means is anything.c. This asterisk is called a wildcard. So I'll just compile all the C files. That'll have the exact same effect, and now I get the executable. And it says the key is blah, blah, blah. The plain text is blah, blah, blah. And the ciphertext is blah, blah, blah. It's all printed out very nicely in hex. So let's say that I just set the ciphertext equal to the plain text. Some of you, this is going to be very tedious, but others of you maybe are confused about what's going on with that hex command. So let's see what would happen if I just printed out the plain text. I would get this. That's because these are unprintable ASCII characters. If you look at which characters are printable, you know, only about a quarter or so of them are printable, so that's why it looks like nonsense. And that's why we need that line right there. Okay, so that gets you started. And so how are we going to achieve what we want to do? Remember, the goal is to compare the differences in state between two plain texts that only differ in one bit as we go down from round to round. So I got a little start on that. I called it Project 3 Solution, but I haven't gotten to the solution part yet, but I've gotten far enough to have something to say about it. So let's go into this new main file, and let me scoot this down so you can see it better, and maybe can I make it bigger a little bit? This might be a smarter way. So you can see this is some new plain text, and I called it M1 instead of the plain text, but it's just these bytes. By the way, these are just these are bytes described as 2 hexadecimal digits. And the reason I picked this message is because I went online and I found a worked example, and so I'm using that example to test my code. So here you can see how DES works in detail. And they give a message, and so this is in binary. I translated the binary into hex, and it's this. And they also pick a key. Where do they pick the key? I don't know. Somewhere right here they pick this key, so I typed in this key in hex, and that's where I get my key. And alright, so if I run this, then it will seemingly just print out the ciphertext, but I have also altered des.c, and I've altered it right here. So if you look in your file, this is you can see it's line. It probably won't be 503 for you because I've written some other stuff too, but it'll be pretty close. Might be like 490 or something. So look down there. And this is the function fencrypt. So this is what actually does DES. And I was looking for the part that corresponds to, you know, all of this is very hard to understand. I don't understand it either. But this is it counts down from 16 to 1. So you know that it's doing the part of the algorithm that is this, like, you know, just the 16 rounds. So whatever's going on in there, it must just be the 16 rounds. And I've added this function, print word32. The reason I call it word32 is in this code, they're using a data structure that's just 32 bits to store the left half and the right half. And I just added a little bit of code so that every time when we go through a round, it prints out what the left state is and what the right state is. And I'll show you the code for that function. This is a link to where I stole it from. By the way, if you steal code from the internet, please always cite it like this. Just put in a link. I can say a few words about how it works. I don't know if you've ever seen a bit mask before, but this is just 32 bits. So this one maybe is look at just this line is maybe the easiest to understand. So think of 32 zeros and ones. This is the final 8 bits, and so when you AND with FF and hex, it's just 1 1 1 1 1. It's all ones for 1 byte, so that's just 8 ones. So that will zero out everything except for the least significant byte of this information. And so the least significant stuff will go on the right, which we're thinking of as being in the third slot in this case. And that's what all of these are doing, except to get the other bytes, so there are 4 bytes in 32 bits, you have to do a little shifting. So if you shift over by 8 and then you apply the bit mask, what you get is the second least significant byte. This is the third least significant byte. This is the last byte. So it's just getting it byte by byte and putting it into this char array. The reason I do that is just because I don't know how to print the damn thing. So I just I wrote this code to do it. And again, I'm calling this this function binary 2 hex because A is just binary data. I call binary 2 hex. I give it the the location of the binary that I want to print, and I tell it how many bytes it is. That code, if you care, sort of a digression. It's in here. I stole it from the internet. Stole it from this site. So if you want to read about what's happening, go here, John's blog, hex encode and decode. All it does is it prints out, you know, raw binary as a pretty hex. So all right, and then it prints out. So this would be the same whether we were printing the left hand side or the right hand side. So I just wrote one function and then I pass in which side I'm dealing with. It says the blank side is in hex blah blah blah, and you can see that I first pass it L and then I pass it R. So let's run this. tt.term, and okay, so the output is still right there. So let's go up to the very top. So this is L0 and this is R0. Maybe it would be more informative output if I put those indices there, but I didn't. So this is the plain text doesn't look like CC00 CCFF. Remember, this is the plain text that we're using. The reason it looks kind of weird like that is because it's already been through the initial permutation. So I was able to use the worked example on this website to get some confirmation that my code is working correctly. So this is CC00 CCFF, and what I got was CC00 CCFF, and this is FOAA FOAA, and what it should be is FOAA FOAA. So that part is right, and it takes them a while to get down to what R1 is. Where is it? Way down here. They explain the S boxes and go through everything, and then they say what R1 is, and what is it? This is EF8, and if you look at my R1, it's EF4. Is that right? Yeah, EF4. That's what it was. It was a 1 in the third place. 4. Yeah, I just did the mental arithmetic wrong. And this is A, and this is 6. And so is that what comes? You've got EF4A6, and probably the other ones are right too, huh? So that's all I checked, and it seems to be working correctly. So this gets you a long way toward your goal. You're going to have to find some way to not just take this message, but also some other message that differs in 1 bit. So just so we're all using the same one, I usually call this M2, let's just change this to 4. So that just changes 1 bit of the input, and so I have no idea what you have to do. I mean, I could figure it out within mere minutes because of my incredible powers of computer programming, but it's pretty open-ended, and I'm just going to check sort of the result. But what I would like to see is every sort of like this, but not saying what the left-hand side and the right-hand side are absolutely. I just care about the difference between the state for these two values. So for the first round through, I don't want to see, or the point is not to find out what the left-hand state and the right-hand state are. It's to sort of find the differences between the two. And what's the logical operator that gives the difference between two binary objects? It's XOR. So XOR is sort of, you can interpret it as being symmetric difference. So it gives the is that what it is? The symmetric difference? The difference is if they're the same. Yeah, anytime they're the same, you're going to get a 0, and every time they're different, you're going to get a 1. So what you want is just the XOR. You want the XOR of the two states as they go through. And as far as how you get that, if you need to like do it once and then store the result and then do it again and then blah, 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 all that's up to you. But I want to see the differences round by round between these two inputs with this key. And that is project 3.